Hey folks, welcome back. This is session 2 of ET 101, Basic DC Circuits. And what we're going to talk about today is numbers. I said, well, it's probably not going to be the most interesting session that you have, but I will tell you this. There are more points wrapped up in today's session than there are in any other session because we are dealing with numbers. Now, how many of y'all heard that there's some math involved with electronics? Yep, see, there's math involved with electronics, and the reason is because, well, number one, the main instrument that we use in troubleshooting electronics gives us a reading in numbers. And the big deal about the meter is there's no point in even pulling a meter out of your tool bag unless you know what it's supposed to say, what the numbers are supposed to be when you put these meter leads in a circuit. See, because if you don't know there's supposed to be 120 volts in a receptacle, if I go measure it and I measure 82, well, I might say, yeah, that's fine. I got voltage there. But the fact is that it's not fine. It's supposed to be 120. And it's reading 82. So if I don't know what I'm supposed to read when I check something, I'm not going to know if it's working right or not, let alone how to go in and find out the fault or the reason it's not working. So first thing we have to do is we have to learn to predict what our meter should say. So there is some math involved in DC circuits. So in order to start you out, I believe in starting out from the very beginning. So first thing I want to know is what is the number system that we use every day for our paychecks, for paying the grocery store bills, everything? What is the name of the number system that we use every day? No, it's not standard. That's not metric. The number system we use every day is called the decimal number system, the decimal number system. Now, actually, while you're here at school, you can learn 4 number systems. The decimal number system is just the one that we use every day. You're also going to learn the binary number system, the octal number system, and the hexadecimal number system. And I'm going to tell you, all of these number systems work exactly the same way. The only difference is the number that they're based on, or their base number, or what they call the radix. So the base number, well, the base number for decimal, our number system, is 10, decade, decimal number system. It's based on the number 10. Then another one that you're going to learn is the binary number system. It's based on the number 2. Then we have the octal number system. It's based on the number 8. And then the hexadecimal number system, which is 6 and 10, or 16. So you're going to be exposed to these 4 number systems as we go through. But the one that we're interested in today is the decimal number system. So the decimal number system. Now, I said all of them are exactly the same, except for one thing, the number that they're based on. Now, decimal is based on the number 10. Now, these base numbers tell us 2 things about a number system. The first thing they tell us is how many symbols there are, or how many digits there are in the number system. So decimal, being based on the number 10, has 10 digits in the number system. The first digit in every number system is always the 0. So the 10 digits in the decimal number system are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. With these symbols, I can represent any quantity that there is. And so that base number tells us how many digits. Now, here's the deal. Any quantity that there is. Let's take, for example, the value 342. Okay, 342. 342. My question is does it matter the order in which we place these symbols to represent 342? In other words, is that 342? Is that 342? Well, no, they're not. So there is definitely an order in which these digits need to be placed in order to represent this quantity. Well, where does that order come from? Well, it comes from what we call a number line. Now, this is the other thing that radix or base number tells us what to do. First of all, it tells us how many digits there are in that number system. The next thing it tells us is it's used as a multiplier for determining column weights on the number line. It's used as a multiplier for determining column weights on the number line. Oh, number line. Well, let's look at this right here, okay? First of all, what happens is we start with a decimal point. Now, our decimal point, like 0 is the first digit of our number system, the decimal point marks the first column weight. To the left of that decimal point is the first column weight on our number line, and that column weight always is the ones column. Now, our base number, 10, is used as a multiplier for determining the next consecutive column weights. So that means I'm going to take and multiply that 10 times that 1 to get the next column weight. So 1 times 10 is, then I have the tens column, and 10 times 10 is the hundreds column, and then 100 times 10 is the thousands column, and it just continues on and on and on. So now, our base number is used as a multiplier for determining column weights on our number line. And our number line, along with our symbols, allow us to represent any quantity that there is. And we're talking about that 342. So how does that all work? Well, if we look at the original, 342, we see the 2 falls in the ones column. And then the 4 falls in the tens column, and then the 3 falls in the hundreds column. Now, we do this without even thinking about it, but we need to be reminded how it works. Well, what happens is it's the digit times the column weight plus the digit times. So we're going to take the digit times the column weight plus the digit times the column weight plus the digit times the column weight. And so if we cipher this on down, 3 times 100 is 300, 4 times 10 is 40, and 2 times 1 is 2. And if I add these up, 300 plus 40 plus 2, that gives me 342. So our number system, the decimal number system, based on the number 10, has 10 digits, and it's used as a multiplier for determining column weights. And along with the symbols and the column weights, we can represent any quantity that there is. And that's the way our decimal number system works. Binary is going to be the same thing, but there's only 2 digits in binary, and the number line is based on 2. 1, 2, times 2 is 4, times 2 is 8, 6. And so the number line and the digit concept holds true throughout every number system. We just use the decimal number system, okay? So this is the way our number system works. Now, we need to talk about exponents because, if you think about it, y'all want to get this, if you want to get it. So if we think about it, I told you on the last session that we're going to be dealing with values of current that are extremely small, thousandths, millionths of an amp. And in order to get these low values of current, we've got to have extremely large values of resistance in our circuit, thousands of ohms, hundreds of millions of ohms of resistance in these circuits. So if we start doing math, if I have a millionth of an amp and I'm working with this value and I've got, say, 68 million ohms of resistance in my circuit, and we deal with values like this, that when we start entering this stuff in on the calculator, look at all those zeros. Those zeros are mistakes waiting to happen, folks. I'm telling you, see, I thought I entered in all those zeros, or I hit the button and it didn't enter in. And so you can see the potential of having incorrect calculations just because you're entering in, well, we need to get rid of the zeros. And folks, let me tell you something, that's what exponents are actually for. Exponents are used to get rid of the zeros, because instead of entering in all those zeros, all I have to do is enter in one exponent and it takes up all those zeros. So it sure minimizes the amount of error that we can have in our calculations. So that's what we're going to do. So what is an exponent? What does an exponent really tell us? Well, here we go. Let's look at that number line again. All right, so we look at the number line. We know it continues on. And so what we're looking at is an exponent. We said it's going to get rid of zeros, but an exponent is actually how many times I multiply that base number to get that particular column weight. So an exponent is how many times I multiply the base number to get that particular column weight. Well, the question is how many times did I multiply 10 in order to get 1? Well, I didn't. If you remember, I said the first column weight to the left of the decimal point on every number line is always the ones column. So I didn't multiply anything times anything to get that 1 value. Okay? So actually the ones column would be represented as 10 to the 0 power. 10 to the 0 power. Sorry about that. 10 to the 0 power. And so how many times did I multiply 10 to get 10? Well, 1 time. So 10 would be seen as 10 to the first power. To get 100, 10 times 10. I multiplied 10 twice. 10 to the second power. How about 1,000? 10 to the third power, 10 to the fourth power. Now, you're starting to see some kind of pattern here. And that's right. It's also how many zeros there are in that value. 10 to the second power is 100. 10 times 2 is 100, which has 2 zeros. 10 to the second power is 100. 10 to the third power is 1,000. And so the exponent tells us how many digits or how many zeros there are in that value. So the deal is, instead of having to enter all those zeros, I can just enter in the exponent that represents all those zeros. Trust me, it's going to be a lot easier entering this stuff on the calculator. Okay? So an exponent simply tells us how many times the base number was used to determine that column weight. And if we look at the column weights, it's how many zeros that we're going to get rid of when we use the exponent. Okay? So now, I hope y'all got the agenda for today, because it's fixing to disappear, because there's something else I need to show you. We're going to look at the number line. So here we go. All right, so there's the number line that we're going to be using. We have the middle part right here that's marked as 10 to the 0 power, and I've got it marked with an amp symbol, an ohm symbol, a volt symbol, and this stands for watts, which is a unit of measure for power, and we're going to get into that later on. But this is the base value, and this is the ones column. Now, going to the left, we increase value, we get to the tens column, the hundreds column, and then the thousands column. And then the 10,000s, then the 100,000s, and then the 1 millions column. Okay, and we keep going 9 and then 12. And then on the other side, where we have negative exponents, these are not negative values. It just means that the value is less than 1. Greater than 0, but less than 1, a fraction of. Okay, and they actually correspond with their exponents on the positive side. So if exponent 3 is 1,000, exponent to the negative third power is 1 1,000th. 1 1,000th, then 10,000, and then 1 millionth, and so on and so forth. So you might be asking yourself, well, why is it that you have these particular column weights emphasized, the ones that are divisible by 3? Why are they the ones that stand out on this number line? Well, I got to tell you, there's 2 ways to do exponential notation. There's what they call the scientific method, and then they have the engineering method. So first of all, the scientific method, and it's all about the format. The scientific method, you can only have 1 digit to the left of your decimal point. However, your exponent can be any value there is. For example, if I wanted to represent the value 12,000 in scientific notation, what I'd have to do is I'd have to take that decimal point, and since I can only have one digit to the left of the decimal point, I'm going to have to move that decimal point all the way down here to behind that 1. Okay, so if that's where my decimal point is going to end up, behind that 1, it becomes 1.2 times 10, and the exponent is how many times I move the decimal point over. So that would be 4. So 1.2 times 10 to the 4th power. Okay, well, that's all fine and dandy, but we don't use scientific notation. We use engineering notation. Now, what's specific about engineering notation is the exponent. See here, the exponent can be anything. It's where the decimal point ends up. Well, with engineering notation, it's all about what the exponent is, and who gives a darn how many digits? Well, so the format for engineering notation is I can have up to 3 digits to the left of the decimal point. Still got to have at least one. Still got to have at least one, but up to 3 digits to the left of the decimal point. And the thing is about the exponent has to be divisible by 3. So that means I'll either be moving my decimal point 3 times, 6 times, 9 times, so on and so forth. Okay, so scientific notation, I can only have 1 digit. My exponent could be anything, but in engineering, I can have up to 3 digits, but my exponent has to be divisible by 3. So that same 12,000 that I had, to convert that to engineering notation, remember, I'm only going to be moving my decimal point in groups of 3. So I'm either going to move it 3 times, 6 times, or whatever. Well, if I leave it here, I got 5 digits, so that ain't cool. So I'm going to have to move it, and all I can do is move it 3, because if I try to move it 1, 2, 3, 4, 5, 6, I'm not going to have any digits, so I'm stuck with moving it 1, 2, 3. So now the correct way to represent that with metric, or engineering prefix is, or notation, engineering notation, is 12 times 10 to the 3rd power. 12 times 10 to the 3rd power. Okay, so I can only move it in groups of 3. So my exponent has to be 3, 6, or 9, so on and so forth. And then when I did move it, it ended up behind the 2. And so I get 12 times 10 to the 3rd power. Okay, so that's what we're going to use. Why are we going to use that? Why are we going to use the ones that are divisible by 3? Well, the reason is because they align themselves with something called metric prefixes. Now, y'all have all heard of metric prefixes. You got a gigabyte of memory. You got 5 gig coming out, and you heard milliliters and micrometers. So we've all been exposed to these metric prefixes. Now we're just going to have to start using them, okay? So those metric prefixes, as they fall on the number line, are 10 to the 3rd is known as kilo, and we have a capital K. 10 to the 6th is known as mega, and we use a capital M. Now look, we're going to use a lowercase m coming up, and it's going to have rounded tops. It's important that my mega have pointy tops. I don't care how big you make that m. If it's got rounded tops, it's not going to be a mega, okay? And so after mega, we get to giga, which is the capital G, and then we move out here to tera, which is a capital T, okay? And so on the positive exponent side, values that are larger than 1, exponent 3 is kilo, we have a capital K, 6 is mega, we have a capital M, 9 is giga, and 10 is tera. On the other side, 10 to the negative 3rd is known as milli, and we use a lowercase m for milli. 10 to the negative 6 is known as micro, and we use the Greek letter mu to represent micro. I call it a funky U. It looks like a U with a tail in the front. So the mu, or the funky U. So, and then after micro, we have nano, which is a lowercase n, and then all the way down here on the end, we have pico. And a little dotted line is just to show you that, yeah, it too is a lowercase p. All right, so this is our number line, folks. This is what we have to know. We have to be able to understand, number one, relative size between what's bigger, a milli or a micro, or what's bigger, 380 micros or one little bitty milli. Well, one little bitty milli is bigger than 380 micros because 1 milli is 1,000 micros, okay? And so we have to understand this relative size. And we're going to be doing conversion problems. I'm going to show you how to do these conversion problems, and then you'll also be getting in your email a worksheet, and you'll turn that in to get your attendance for today. All right, so we're going to be doing metric conversions. So what am I talking about? Well, for example, I tell you what, this is a good time to take a pause. We'll come back and we'll do some more, and then we'll look at the calculator. All right, good deal.